Music has an undeniable effect in our lives. It can affect our emotions, change our movements, influence our vitality, and impact our daily life. This work describes a human-computer interface used to characterize the evolution of the stochastic signatures of physiological rhythms across the central and the peripheral nervous systems in the presence of music. Through this project, we systematically examine the individual's biorhythms as they change with the music. We can then identify which music best changes the biorhythms of the individual, so they become entrained with this external beat. Much as physical entrainment is taking place here, we are trying to capture the physical entrainment of the body's biorhythms with the rhythm of the music. With that in mind, we will explore different external influences on the individual's biorhythms through different experimental conditions. We asked our participants to naturally walk under 5 different conditions. The first, with eyes open and no music in the background. The second, with their eyes closed and again, no music in the background. The third, with their eyes open and our choice of music in the background. The fourth, with their eyes closed and again, our choice of music in the background. The fifth, with their eyes open and their favorite song in the background. We use the Inobio EEG system to record EEG data and the extension ECG cable to register heart rate data. The face-based motion capture system was used for positional data of the participants' body parts. For each data type we collect, we smooth it to reduce instrumentation noise. Then, the signal was upsampled to reach 44.1 kHz, such as to be comparable with the music signal, which has the highest frequency among the 3 signals. Finally, we mean shift to sample negative values and estimate the micromovements. We apply the same data processing for speed, heart rate, and music data. But what are micromovements? The micromovements are the original data peaks normalized to range in the real line along values between 0 and 1. This standardization of the data permits comparison across participants with different physical and anatomical measurements and offers a new way to integrate and compare data from various instruments. To better understand the compressive nature of the data, here is the original audio file. And here is the audio's micromovements. A total of 22 different time series of micromovements were generated for music, heart, and the 20 body parts. We converted these micromovements to sound and applied methods for music features extraction. First, we estimated the envelope to review the global outer shape of the signal. Then, we estimated the autocorrelation to study the periodicity of the signals. The outcoming 22 sequences build the autocorrelation matrix. Here is the autocorrelation matrix with the various signals. You can see the music, the heart, and the body. Here, we separate the maximum autocorrelation occurring at different lags across the body, signaling the codependency of present statistical events with past statistical events, and the minimal autocorrelation at different lags across the body, signaling statistical independence of present events with past events. Here are all of the results of all of the conditions. As you can see, the favorite song wins, with a clear separation between the independent statistical processes as shown by the minima autocorrelation values and the codependent statistical processes as shown by the maxima autocorrelation values across the heart and the body. Now that we know how to detect and parameterize the external sensory input that best entrains with the bodily biorhythms, we can use this information in closed loop and extend our human, co-adaptive, interactive computer interface to help guide the nervous system to selectively entrain with the environment. This form of quantification can be an outcome measure of nervous system's performance, and as such, it has therapeutic implications.